Спасибо за приглашение. Здравствуйте, друзья. Как вы думаете, я хотел бы говорить по-русски, но был, как обычно, выбор, либо подготовить статью по-русски, доклад по-русски, и для этого мне нужно было целая неделя, или попробовать улучшить статью. И, как обычно, я выбрал, я шел во второй дороге. Bon, okay, so I speak English. Okay, so the topic is zero cycles on the dead Pezzo surface, on dead Pezzo surfaces. And I'm very glad to speak in this Исковskих seminar. So there's a preprint on the archive, and an improved version of that preprint is on my webpage. So in 1952, Tony Springer proved the following. Take a quadratic form of a field. If it has a non-trivial zero over a field extension of the ground field of odd degree, then it has a non-trivial zero over the ground field. So if a quadratic has a point in an extension of odd degree, it has a rational point. And okay, here is at least one proof in this whole thing. You may assume that the extension is simple, because otherwise you have a tower of simple extensions of odd degree. You write it as k bracket t divided by p of t reducible, and then you write that there's a solution. So you write it in terms of polynomials. Q of R0 of t, Rn of t equals p of t, q of t, where p is your polynomial, and this R0 of t, Rn of t are of degree strictly bigger than degree of p. They're not all zero. And then you look at the degree on this side, it's at most 2d minus 2, here is d, so the degree of q of t is smaller than the degree of p. But on the left-hand side, it's of even degree. Here you have odd degrees, so inside q of t, there's a factor of odd degree, strictly smaller than the degree of p, and so you go down in degree. Right. So here's an exercise in the same spirit. You can keep it for your students. So take an integer n at least 1, take a quadratic form over a field k, and take a polynomial of degree 2r. And assume that the affine equation, p of t minus q of x0 xn equals 0, has a solution and extension of degree capital Q over k of odd degree. Okay, so q is quadratic and p is of degree 2r. And then either the leading coefficient of p is represented by q over the field k, which in fact means that this hypersurface has some rational point at infinity, or the equation has a solution in the field extension capital K of odd degree at most r. Okay, so you go down in the degree. The x0, xn were in big fields, but you can go down, and in fact you can go down to at most r. So it's, if you want, it's a special family of quadratics over the line. Okay, now is a nice theorem. This is preparation. Suppose you take an intersection of two quadratics, arbitrary intersection of two quadratics, could be very singular and whatever, defined by phi x0 xn equals 0 because psi of x x0 xn. Suppose it has a rational point over an odd degree extension of little k, then it has a rational point over k. The special case of dead Pezzo of degree 4, which is in P4, I'm sorry, was proved by Corey in 1977. And that theorem here is an immediate consequence of Springer's result and the following theorem, which is proved by Armand Brunner, who is with us, and David Leap in characteristic 2. So the theorem says, suppose you have two quadratic forms in the same variables with coefficient of the field k, then they have a common non-trivial zero of a little k, if and only if the quadratic form phi plus t psi has a non-trivial zero of the rational field k of t. So you take the pencil through the quadratics, and you take the generic quadratic in the pencil. So the generic quadratic in the pencil has a rational point, if only if the intersection of the two quadratics has a rational point. So if you combine that with the Springer theorem, you get this result here. So one would like to produce classes of algebraic varieties over field K with the property that if X is zero cycle of degree 1, which is, in other words, says that the GCD of the degree is the finite field extension for which the variety acquires a rational point is 1. So you look at the degrees of closed points and you compute the GCD. If it's 1, you would like actually a rational point to exist. Okay. So that property, which I call star, I promise there will be no further property star in this talk, holds, for instance, for plane cubics in P2K, arbitrary plane cubics in P2 over any field K. And it's been proved, it's been the subject of a lot of investigation for principal homogeneous spaces of connected reductive linear algebraic groups. The commutative case is easy, but the problem is when it's non-commutative. So it's been proved in many cases. Yes?
What about principal homogeneous spaces over abelian varieties?
Well, it's in that case, it's always because you have a norm map, you see.
Okay.
That's the point, is with when it's non-commutative, you don't have norms. That's the whole problem. Okay, you have H1KA, you go to some field extension, then you go down, you get measured by the degree. So then you get co-prime degrees, and so the class is scaled by 1, and therefore it's got a rational point.
Okay. Thank you.
And that works for tori as well, for instance. I mean, it works for commutative groups. Okay, now the thing is that, very surprisingly, there are counterexamples to this property star for projective homogeneous spaces of semi-simple groups. So if I remember well, the field she uses is a field like a function field, one variable of a periodic field. Now, that property star is an open question for cubic hypersurfaces. This question was raised by Cassels and Sundayer many years ago. In this case, the question is simple. You have a cubic hypersurface in Pn, or cubic form if you want to speak in terms of forms. You suppose it has a point in a finite field extension of degree prime to 3, because obviously that it has a point extension of degree 3 or 1. Does it have a rational point in K? And so the question was studied by Daniel Corey, whom I knew well and with whom I worked, and who unfortunately died in 2015. He worked on this in his thesis in Cambridge, Britain in 1974. So here's it was published in 76 in Acta Arithmetica. And you see CS, which stands for Cassels and Dyer here. So there are two main theorems in this thesis. So the first one, on which I will speak very little, but I really want to speak about it a little bit because it's very nice. Suppose your field K is the field of fractions of a complete discrete variation ring with real field kappa. If property star, that is, which I mentioned, okay, if you have a point and extension of degree prime to 3, then you have a rational. Suppose it holds for cubic hypersurfaces over capital K in any dimension, then the same property holds for cubic hypersurface over K in any dimension. Okay, so that property is inherited by passage to complete DVR with the field you started with. So that is proved by a delicate study of possible bad reduction of cubic hypersurfaces, extending earlier work of Demyanov, 1950, Lewis, 1952, Springer, 1955, who had proved that over a periodic field, if you take a cubic form in at least 10 variables, it always has a non-trivial 0. But by kind of reductions like the one you know very well for quadratics, but it's harder. And this study in Corey's paper, I think it's not studied well enough because people have a series of how rationally connected varieties degenerate, but I don't know a modern thing that would prove what is proved there. So in any case, a corollary is that a corollary of this one here is that the property star holds for arbitrary cubic hypersurface of a periodic field, because for cubic hypersurfaces over a finite field, it's an easy property. So the only case to consider is three variables, 2 or 3 variables. I mean, starting from 4 variables, finite field is a C1 field, so you automatically have a 0. Right. So, sorry. So the talk is concerned with the second main theorem in Corey's thesis, which I now write, which in this talk I call theorem A. You take a smooth cubic surface of an arbitrary field, and you assume it has a rational point in the field extension of degree prime to 3. Then it has a rational point in either of degree 1, and then you're happy, it has a rational point, or possibly just one of degree 4, or possibly one of degree 10. Okay, and these possibilities are not excluded. Okay, so we get 1, 4, or 10, and that's it. Okay. So now my plan is the following. I'm going to describe the main points of Corey's proof, and then we'll see other cases where we can do the same kind of arguments, and I will not go into the details of the arguments in the next cases. And I'll show you the improvement which I've made on Corey's argument. This will come after I describe his proof. So Corey uses curves of low genus lying on the surface. And the curves he uses, one doesn't know whether they are smooth or even irreducible. And so what he does is that he constructs these curves, which he finds in linear systems, and he says, oh, okay, well, if they're reducible, then I will produce another argument, or I'll manage all the same. Okay? So I will explain a general method to dodge this part of the argument, and with the added flexibility, I produce new results without much pain. So let me remind you, I mean, I think everybody in this seminar knows all these notions, but I write them, I go through them quickly. What is a zero cycle on the variety over a field K? It's a finite linear combination with integral coefficients and some NPP, where the P are closed points. Okay, so closed point is its point which has a real field, which is a phi extension of the ground field. And a cycle is called effective if all the coefficients are non-zero, non-negative. The degree of such a zero cycle is the sum for all P of NP times degree of the closed point. There's a notion of rational equivalence on the group of zero cycles. Each time you have a proper map from a normal integral curve to X, and you have a rational function non-zero on your curve, you take the divisor of that function that produces a zero cycle on C, and you push it down in the usual way, down to X. Okay? And so the rational equivalence is the equivalence which is generated by all the possible P, C, and F. If the variety is proper, the degrees of a zero, the divisor of a rational function on a proper curve is 0. So we have an in-use map from Z0 of X modulo rat to Z. She's taking the sum of the degree here. The image of that map is an ideal of Z spanned by index of X, which is the GCD of the degree of closed points. And the kernel is denoted, there's a D missing, A0 of X. So again, this seminar is not the proper place for reminding something. Anyway, so we're asking about zero cycle, what we can say, what we can do with zero cycles. So for curves, we're quite happy because we have Riemann-Roch on a smooth projective geometrically connected curve of genus G, which says that in particular, if I take any zero cycle of degree at least equal to G and gamma, then it is rationally equivalent to an effective cycle. Okay, immediate consequence of Riemann-Roch. Now let's discuss surfaces, because that's what we're going to look at, curves and surfaces. So we take a nice surface, smooth, projective, geometrically connected. Let capital K be the class of a mechanical divisor. There will not be confusion with field extension, don't worry. And if you take D, an effective divisor on X, you define the arithmetic genus formally by the formula D times D plus K over 2 plus 1. Okay. You take this plus 1. And if D is a smooth projective curve of genus G, geometrically connected, then the P of D is actually the genus of that curve. And the other thing is, if you have on a surface, you have like on a variety, but in because I'm discussing the case of surfaces here. If you take an inevitable sheaf on your surface, you have the Euler point characteristic is 0 of XL minus H1 plus H2. And you have the Riemann-Roch theorem that tells you what is the Euler point characteristic of L. It is L times L minus K divided by 2 plus the Euler point characteristic of OX. Well, you know that HI of XL is equal to H2 minus I of X K minus L, c'est la dualité. Here I mentioned something which actually is not needed for the arguments which follow, but that if you want the exact value in the end, you're happy. If L is ample and h1 of x minus L is 0, then in characteristic 0, Colliot tells you that this group is 0. This group is 0. This dimension is 0. And finally, if x is geometrically birational to P2, these are the varieties we're going to be interested in. This quantity here is just 1. Right. So from now on, to be on the safe side, I'm going to assume characteristic of k equals 0. And if I followed fashion, the new fashion is to write capital K like this to say without saying that the characteristic is 0. But I won't use that. Okay, now let me describe Corey's method for a smooth cubic surface in P3K. We assume that x is a closed point of degree d prime to 3, and we want to compute the least such integer. Okay, in the end, we're going to show that it's either 1, 4, or 10. Okay. So if d is 1, we're happy, there's a rational point. If d is 2 on a cubic surface, we know very well how to take a point of required extension. It's conjugate the lines through the 2 points. You get a line of a little k, and the third point of intersection is a rational point. So in fact, d is 1. So let's now assume that d is prime to 3, and that d is at least 4. And P be a closed point of degree d. Now, we have this closed point of degree d. On the surface, we pick a closed point of degree 3, for instance, by intersecting with a line. Okay, so now we have a point of degree d and a point of degree 3. And so the idea in Corey's paper is simple. Try to find a curve of genus as low as possible that goes through Q and P, and try to use Gerner on the curve to descend the degree of an effective cycle. So let n be the smallest integer, such that there exists a surface in P3 of degree n, cutting out a curve gamma in x, which contains both P and Q. So you compute on the surface, this is a very easy case of Fermat, the dimension of OX of n, and you find 3n times n plus 1 over 2 plus 1. Now, in my description of Corey's argument, from now on, I'm going to assume that we can produce such surfaces that cut out a curve gamma, which is geometrically irreducible and smooth. This is the point one point I want to improve upon later. Okay? How to get this assumption for free. Okay, on this curve, we have a point of degree d, which is prime to 3, and a point of degree 3. So we have a 0 cycle of degree 1. You compute the genus for that curve, and you find that it is 3n n minus 1 over 2 plus 1. So here we had 3n n plus 1 over 2 plus 1, and now we have 3n n minus 1 over 2 plus 1. So if, on the one hand, this condition is fulfilled, 3n n plus 1 over 2 minus 3 is at least d, then what you get is that the dimension of linear system is bigger than d plus 3 plus 1. Okay? And so you can find a surface at degree n, which cuts out a curve gamma, which we assume to be smooth, passing through the point of degree d and through the point of degree 3. There's enough room. If, on the other hand, the d is at least 3n n minus 1 over 2 plus 4, then if you take d minus 3, you find that it is at least equal to the genus of gamma. Okay? So if this is fulfilled, you find that the 0 cycle P minus Q on that curve is rationally equivalent to an effective 0 cycle of degree d minus 3, strictly smaller than d. Okay, and that's prime to 3, so we have a contradiction. So in these cases, so if these two inequalities are fulfilled, we managed to prove that in fact our assumption was absurd. That is, we could have gone down on the degree from the very beginning. Okay? So the only problem is it works for any integer d prime to 3, which lies in an interval of that shape. D switched in between this value and this value. So intuitively, this is quite possible because here we have n minus 1 and here we have n plus 1. But there are specific values of d where it doesn't work, okay, where we don't manage to make the argument work. And in particular, for the integers d, which are of the shape 3n minus 1 over 2 plus 1, Corey's idea at that point is to use to impose on the curve singularities. So what he does is that he takes curves which pass through the point P of degree d, and which have a double point at the close point of degree 3. So the genus of the curve in the linear system drops by 3, because we have 3 double points geometrically. But the dimension of the linear system of interest drops down by 9, because we have 9 linear conditions. Okay. And so what happens is that for d of this shape with n at least 4, there's enough room. But in the case n equals 2, it equals 4. And in the case n equals 3, d equals 8, there is not enough room. And so that's where the argument stops. And that's why the conclusion of Corey is that on a cubic surface with a close point of degree d prime to 3, the least such d lies in 1, 4, 10. And this question has been open for 45 years now. Can one eliminate 10 and 4? 10 or 4 or both? Right, so this is conclusion modulo the good position argument. Okay, any questions on this? Is very, I mean, the idea is simple. You have to pay attention when you compute your dimension of the system, your genus, and this clever argument of imposing these singular points to manage to get down on the genus. One thing you should imagine is that this is very specific to cubic surfaces. If you try to do that with quartic surfaces, unfortunately, you wouldn't get this miracle that you have this nn plus 1 on the left and this 3nn minus 1 on the right. What you would find is that you would find something like n square on the left-hand side and the same n square on the right-hand side, and so you couldn't do anything. And this is no wonder, because we'll see later that this kind of argument can be used to show that zero cycles are spanned by zero cycles of small degree. And it's well known that if you take a quartic surface over the complex field, because of Bloch's famous theorem, you cannot do these kind of things. Okay, so now the above argument assumes that the curves gamma found in the Euler system are geometrically reducible and smooth. So as I said in his paper, Corey discusses the possible singular and even reducible curves which may turn up, and manages to get down to 1, 4, or 10 also in these cases. And it's clear that such cases may occur, because if you consider the simpler problem of finding in the plane a smooth plane conic going through a close point of degree 3, well, if your close point in the first place happened to lie on the line, then you cannot find a smooth conic, right? You have to move your close point of degree 3 to be in a position to find a smooth conic through it. Okay, so now I explain how discussion of how to avoid the discussion of Jared cases. And I reveal on this slide what are the main ideas. So one available, use result of the type. If there's a k rational point on a k variety x of the type in the study, for instance, in this case, then the k rational points are Zariski dense. And this is of interest even if you start with a cubic surface, for instance, which has no rational point to start with, because you look at what happens over a field extension. And over that field extension, you have a close point of, say, of degree d. You look at this close point. Over that field, the cubic surface acquires a rational point. So over that field, because of what we know about rational cubic surfaces, it acquires lots of rational points. So you can move your point around. Okay. The second idea, which is not very original for this kind of problem, is to use Batinis theorems. But it's Batinis theorems where you're imposing your linear system to go through some points. So it's not standard things which you find in literature. Then there's another idea, which I've seen before, which is to replace K by a large field. So you go over, you take your variety over K and you go over to the field K double parenthesis T. So because the field is large, I'll come back to this, over a large field, if you have one smooth rational point, then you have lots of rational points. Okay. And what happens is that for the problems which consider here, to prove a result for a K variety X, it is enough to prove it for the K double parenthesis T variety X cross K, K double parenthesis T. So that's a new trick for this kind of problems. Okay, so now I start with the variation on Batteny. So my reference for Batteny is Giannolo's book. you take any field. I said fields of characteristic 0. So I don't want to go into the discussion. So take a smooth projective geometrically connected K variety. Take a K morphism. Assume the image has dimension at least 2, and that image generates projectively the projectives P and K. Take an integer R, which is at most equal to n. Then there exists a non-empty open set U in X cross X R times, such that for any field L which contains K and any L point lying in U of L, there exists a hyperplane H defined over L, whose inverse image in XL is a smooth geometry integral L variety which contains the points P1, PR. Okay, so R is at most n. So example, if you take P2 and identity of P2 to P2, and you take R to be at most 2, if you take two rational points, well, you can find a smooth curve through these 2 points. But that's a very trivial case. Okay? So the point here is that I never assume that X is a rational point in this statement. You see? So the statement is that you have some open set, and if you go over to some field where there is an L point, then you can apply your result at the level of L. Okay? So that's a statement about family of rational points. And now we're going to look at closed points. So we take X to be a smooth K variety, M an integer. And then we take the product of X by itself n times, consists of m tuples x1, xm, sorry, with xi, no, sorry, and we look at the open set, which is the complement of the approximate diagonals. Okay, so the n tuples where all the xi different from xj. Then the symmetric group on m letters, x and w, and the quotient is a smooth K variety, denoted sim m sep x. That variety parameterizes effective cycles of degree m, which are separable. By the way, I was looking for literature on how sim represents 0 cycles. And in fact, there are quite good papers on this in literature. In particular, I found that the thesis by David Reed, which is online. But here we're just using the separable part, which is quite easy. So now I have a 0 cycle version of the previous theorem. Previous theorem was about product of X by itself R times. So now what we do is that we take a smooth projective geometrically connected variety. We have a K morphism, make same assumption that the image has dimension at least 2, and it generates P and K projectively. And then we take natural integers, S1, St, whose sum is at most little n. And then the statement is that there exists a non-empty open set U of the product sim S1 sep X cross sim St sep X, such that for any field L which contains little k, and any L point of U corresponding to family Zi of separable effective 0 cycle respective degrees Si, okay, k point here corresponds to an effective 0 cycles of degree S1 over the field we're looking at. There exists a hyperplane whose inverse image is defined over L, is a smooth geometry integral L variety which contains the points of the support of the cycle sum of the Zi. Okay, same comment. I'm not saying that U of L is not empty. If U of L is not empty, then we find this. Okay, right. Okay, so that's Batteny theorem for finding hyperplane sections, inverse images of hyperplanes, which contain a given set of closed points. Okay, now let me define some new definition. Take a field of characteristic 0 and a smooth projective geometrically connected variety. So in this talk, I'm going to introduce this notion that is not a very good word. I mean,
yeah, excuse me, I have a question about previous slide.
Yes.
And why to take several copies of symmetric product and not to have one zero cycle?
Because I'm going to start with a close point of degree S1, a close point of degree S2, and a close point of degree ST.
Yeah, but anyway, you are formulating it that you are having a hyperplane section passing through a zero cycle, which is
no, but you see, if I took the whole thing,
yeah.
Let's see, for what I want to do, you're quite right. You're probably right. I mean, for what I want to do, that probably would be just as good. Yeah.
Yeah. So sorry, this was yeah. Yeah, maybe it is a different open subset.
Well, yeah, you get a different, but it doesn't matter. In fact, it doesn't matter for the proof to follow. Of course, if I take sim step for the whole thing, I'm taking something a bit smaller. But no, it doesn't matter for the proof to follow. Yeah, okay, it's purely psychological. It's because I'm going to start with this close point of degree S1 and this close point of degree ST. Okay, thank you. Okay, so we say that a variety X has the density property if it satisfies the following thing. For any finite field extension where it acquires a rational point, the set of L points, the L rational points, are Zariski dense in X over in XL. XL is X cross KL. Okay. And I'm going to give examples in a minute. In fact, immediate examples is cubic surfaces, even cubic hypersurfaces. So cubic hypersurface of field, smooth cubic hypersurface of field characteristic 0 need not contain a rational point. But as soon as you go over to a field over which they have a rational point, in fact, they're unirational, therefore they have rational points, in fact, lots of rational points. Okay, and then we say that X has the R density property if it satisfies for any finite field extension L over K and any point P in X of L, the set of points of X of L which are R equivalent to P on XL is Zariski dense on XL. Now, possibly not everybody knows what R equivalence is. So on the variety over field K, say projective variety over field K, you look at the equivalent, the elementary relation between two rational points. There's a rational map from P1K to the variety, such that the two rational points are the images of rational points on the P1. And then you take the equivalence relation, which is generated by this. So intuitively speaking, you have chains of rational curves going from P to Q via some other points. Right, so smooth cubic hypersurfaces in P and K satisfy both properties. I mean, the second one is not completely obvious, but it uses unirationality plus all the symmetries which you can have on cubic hypersurfaces, symmetry with respect to a rational point. Okay, now here's the Batinis theorem for varieties which have density properties. So we take a field of characteristic 0, we take just the same situation as before, smooth, projective, morphism, image of dimension at least 2, which generates P and K, and we take close points of respective degrees S1, ST, such that sum of the degrees at most n. Then if X satisfies the density property, then there exists a hyperplane H over K, whose inverse image is smooth geometric integral, and which contains effective zero cycles Z1, ZT of respective degrees S1, ST. Okay. So we started with some close points, and now we've replaced them. We didn't know whether there was a smooth hypersurface that contained them, but now we've found effective zero cycles of the same degrees as the close point we started with, through which there's a smooth projective hypersurface that goes. Okay. If X satisfies the R density property, then one may do better. One can do the same thing, except that one can arrange that the Zi, each Zi is rationally equivalent to the zero cycle Pi. Zi is of degree Si, Pi is of degree Si. Okay. So we can find this hyperplane section such that there are zero cycles with the property that Zi is rationally equivalent to Pi. Okay, that's a Batteny theorem for varieties with density properties. Now, here's a definition by Pop, Florian Pop. A field is called a large field. In French, it's fertile. And in Russian, you have the choice between shirokoye polye or pladatvornoye polye. Then the set of rational points is Zariski dense. So as soon as you have a rational point, you want the set of rational points to be Zariski dense.
Плодородное, right?
Plodavtornoye, correct?
Плодородное.
Tornoye.
Not
Tvornoye, you're right, Tvornoye. I wrote it correctly, I pronounced it incorrectly. Tvornoye, thank you. Thank you, Yuri. Okay, so the statement is, you have a variety, the field is large, as soon as you have a rational point, the points are Zariski dense. For instance, take a smooth variety over the rails, it is large. You need not have a real point, but if you have a real point, then the real points are Zariski dense. Okay. If a field is large, then any finite field extension of F is large. Thus, any smooth trivially connected variety of a large field has the density property by definition. So triviality with this definition. And now an important point is that if you take any field and you take the function, the field of power series in one variable over the field K, F is large. And in fact, it's a general property if you take the field of fraction of a complete DVR residual field of field. That's a large field. And there's a Batteny theorem of a large field, which is very much the same as the previous one, except that now we, so the assumptions are the same as before, okay? And then the statement is that if the field is large, then we can guarantee that there's a hyperplane which cuts out a smooth, smooth hypersurface on your X, and which contains effective zero cycles of respective degrees S1, St, okay? Starting from the fact that you had given close points on your X of respective degrees S1, St. So by changing the P1, Pt, you produce zero cycles, the same degrees, and then a smooth hyperplane section that passes through this. And if, moreover, if you take X to be geometrically rationally connected, in the sense of Colliot-Thélène, then one can ensure that for each I, the zero cycle Zi is rationally equivalent to zero cycle Pi you started with. Okay, the point is that, do I say that? Yeah, okay. For the proof of A, the family P1, Pt defines an F point of the smooth connected variety CMS1S of this product. Since F is large, any non-empty Zariski open set of that K variety contains an F point. Okay. So we're happy. I mean, we take the open set which is produced by Batteny, and then you find an F point in that open set. For the proof of B, which involves these rationally connected varieties, what you use is that for any F point on a smooth projective geometry separately rationally connected variety over a large field, the set of F points which are R equivalent to P, there's an R missing here, and in particular rational equivalent to P is Zariski dense in X. And that's the theorem of Colliot in 1999, who developed the deformation method, which people know very well of the complex field. He developed it over a p-adic field, but in fact over a large field. So if you look at his proof, you see that you get this result. If you have a rational point on a smooth rational connected variety over a large field, if you talk with any rational point, the set of points which are R equivalent to it is Zariski dense. Okay, so now here is I told you there was a list of ideas, and the easiest is this one. Take a field K and take the field of rational, formal power series field in one variable over the field K. Take a proper variety of field K. And now the GCD of degrees of close points for X over K coincides with that for xf over f. Okay, you want to compute the index for x, it's enough to compute it for xf. And it's pretty obvious why you can do that, because if you have a close point on x, it leads to a close point on x cross k double plus t. But if you have a close point on x, k parameters t, you spread it out over k double bracket t, and then it may break up into sums of close points. But since we're interested in GCD, you get what you want. Okay, second one of the same style. You take an integer r, the smallest degree of a close point of degree prime to r, which is the kind of thing we're after. This was 3 for cubic surfaces, which is also the smallest degree of an effective zero cycles at degree prime to r, coincide for x over k and for xf over f. Third property, if you take a set of natural integers, if the char group of f0 cycles on xf can be generated by the classes of effective cycles of degree d in I, then the same holds for x. So you're trying to see whether you can generate your char group of 0 cycles by small points of small degree. And d, if every 0 cycles on xf of degree at least d is rational equivalent to an effective cycle, then the same holds for x. So this is the analogous property of what we saw for curves of genus G. Any 0 cycle on a curve of genus G of degree at least G is rational equivalent to an effective cycle. And we'd like to have such properties on other varieties. Okay. Now,
are you assuming that the X is smooth here?
No, no, this is completely formal. You see, that's the point. Just think, I mean, the whole point is that you take x cross k double bracket t, and you look at x, the special fiber and the generic fiber. And rational occurrence is fine. You can specialize rational occurrence. Okay?
Yeah, thank you.
Okay, and then once equipped with this Batinis theorems, one can run Croy's proof using only smooth projected curves in the linear system of interest. And because there are 2 types of Batteny, there are 2 ways to do this. One may use the density property of smooth cubic surfaces. That is the property that as soon as they have a rational point, the rational points are Zariski dense. And then one apply Batinis theorem A for varieties with this property. Or one may reduce to large fields by replacing k by k double plus t, use Batinis theorem A for large fields, and then use the fact that the statement of the theorem for x k double plus t over k double plus t implies it for x over k by these easy statements I just wrote down. Okay, so that's well, that's the way to do Croy's theorem in a sort of smooth way, if I dare say. So an important point has been to be able to move the given effective 0 cycle through which one wants curves of a given linear system to pass and simply be smooth. So if you wanted them to be, this linear system, the curves in the linear system be smooth, we had to move these points. And that's what we can do in 2 different ways. Right, so this flexibility, equipped with this flexibility, we can start thinking about proving other theorems and other varieties without going through the effort of thinking of all the possible degeneracy cases. Okay, so let's look at that Pezzo surfaces of degree 2. So we're going to use Batteny of a large field to prove this theorem. Take a delta Pezzo of degree 2, that is a double cover of P2K ramified along a smooth quartic. If there exists a close, so of course there's a close point of degree 2. So we wonder what happens if there's a close point of odd degree. Then what happens is that in fact we can prove that there's a close point of degree 1 or 3 or 7. So this is the analog of the 1, 4, 10 of Corey. So in the proof, just as for cubic surfaces, in certain cases, the cases where we need to put the singular points, one need to blow up, if you want to do it very nicely, control the linear systems. The best way is to blow up the points where you want the curve to be singular. So you get new surfaces, and you want to know whether some line bundles are ample, okay, or very ample. And one way to do it without thinking is to use Ryder's criteria over field of characteristic 0. Okay, that's a technical point. Okay, so for that purposes of degree 2 is a k-rational point, not in a very special situation. K-unit ratio is known. So many people have worked on this. So I mean, there's something in Manin's book, and then Van Looy worked a lot on this, also with I think with Salgado and with Alvarado. But there are a few cases which are left over where the rational point lies on, I don't know, many exceptional curves at the same time. Anyway, the trick with
I think
large
also
field,
the
sorry?
ramification curve as well, right?
A ramification curve as well, yeah. So so it would be a bit a nuisance, but because of this trick with large fields, we can use this Batteny theorem of a large field. I don't have to think about this. Okay, we use the second, the one with of a large field, and then we get the result. Now, in this special case, I told you that for Corey's theorem, 1, 4, 10 is open. Well, for deficits of degree 2, 1, 3, 7 is not open. There are examples of surfaces of degree 2 with a close point of degree 3, but no rational point. So this was mentioned in a paper of Collar and Mella in 2017, and Collar shown, I mean, it was just hinted at, I mean, the statement was made, but not the details, and Collar showed me the details. So you take a field K, so here's how you build a counterexample. You take a field which admits a quadratic field extension, a cubic field extension, and a quintic field extension. In the plane, you pick up a conic with a smooth K point, and then you find a smooth quartic curve in P2, which intersect the curve C, the conic C, in just 2 points, one of degree 3, one of degree 5. So there's some little work to show that you can, I mean, it's clear that there isn't enough room because this is imposing just 8 conditions on your pencil of quartics in the plane. So there are lots of quartics. The thing is to prove that there's a smooth one, so you have to work a little bit. Anyway, or maybe you have to move the points A and B. I have to sort this out, but anyway, I'm sure this works, okay? So now take the smooth diapers of degree 2 defined by the equation Z square. This is bihomogeneous. U, V, W are of degree 1, and Z is of degree 2. Z square minus A, C of U, V, W. C is the equation for the conic to the square, plus T, Q of U, V, W. Q is the equation of the quartic. Okay, so that's diapers of degree 4 over the field K of T. And it's got obvious rational points of degree 3 and 5 at the intersection points of C and Q. But if you do reductions modulo T and then modulo T square, you see that there's no F point. Okay. So you do have examples where this 3 cannot be avoided. Very sad. All the more so as the problem doesn't arise for deficits of degree 1, because for deficits of degree 1, you all know that there's a rational point. Okay.
And can I ask a question about 2? And can we also construct an example of the Pezzo surface of degree 2 which does not have odd degree points at all?
Which doesn't have what?
Does not have points of odd degree at all.
Sure. I mean, you take a double cover of P2 over the rails, which has no real point.
Which has no real point, right?
There's no real point, yeah.
Okay.
I mean, I take Z square, you know, I take a double cover, I take Z square plus, I mean,
yeah, I see, indeed.
Z square plus X4 plus Y4 plus T4 equals 0. Over the rails. Okay? There's no real point, so there's no point in an odd degree extension. You agree?
Yeah, I totally agree.
Yeah.
Very few extensions and no points over the base field. Yeah.
Okay, so now, okay, here's so we had theorem B, now is theorem C, where we're going to use Batteny over large field, or either of these two. And when we're going to use the theorem, the B version. That is the one which involves R density. So we take a smooth cubic surface and suppose it has a rational point. We suppose it has a rational point. Okay. Now, the first statement is that if I take any effective zero cycle of degree at least 4 on X, it is rationally equivalent to an effective cycle of the shape Z1 plus RQ, where R is positive and Z1 is effective of degree at node 3. So I can subtract copies of Q and remain positive at least until I hit something of degree 3. So that statement A, do I say something about the proof? No, I don't say anything about the proof. Wait a minute, do I say anything? No, I don't say. So okay, I'll say something about the proof afterwards. So A implies very easily B and C. Every zero cycle of degree 0 is rationally equivalent to the difference of 2 effective cycles of degree 3. C, the Char group of zero cycles on X is generated by classes of rational points and of closed points of degree 3. And then there's statement B, D, which doesn't follow readily from the first ones, which is that every zero cycle on X of degree at least 10, no, this is not effective, is rationally equivalent to an effective zero cycle. And so the idea here in the proof is the same as in Corey's proof. You start with your effective zero cycle with degree at least 4, and then you have your rational point at your disposal. So you find a hypersurface of degree as small as possible going through your effective cycle and through the rational point. And because you have a rational point, you can do better than you could do with a point of degree 3 in Corey's argument. So that's why we get down to something better. Okay. And so you take a curve which goes through your effective zero cycles and this rational point of genus as low as possible. Use Riemann-Roch, and then you go down. And this is what comes out. And for the deep part, you have to go through the process again. It doesn't follow readily from what you had before. So this one is an analog of what we had for curves of genus G. Okay, there's starting from some degree, any zero cycle is rational going to an effective zero cycle. So let's make a parenthesis, because I've been told, because is that right, that I can talk more than 1 hour. Is that right?
Yeah, sure. That's what people usually do.
Okay, so this is the Russian style. I'm quite happy, but I won't be too long. Don't worry. For those who were prepared to listen for just 1 hour. Okay, so let me do a parenthesis, which I've added because I knew I could speak more than 1 hour. It's a parenthesis of p-adic fields. So if I start with a cubic surface of a p-adic field, I can use K unirationality and symmetries to prove that the set of Oricons classes is finite. The idea is very simple, is that because your surface is K unirational, you have a rational map from P2 to X, which is étal over some open set. So you have an étal map from open set of P2 to X. So the image of the rational point on the open set will be some open set in X of K consisting of rational points, which are all equivalent on X. And then you can move around this big open set of equivalent points by symmetries around the surface. In fact, this argument was shown to me by Sven and Dyer many years ago. Okay, so the set of equivalence classes in this case is finite. Okay, now because there are only finitely many field extensions of a given degree for a p-adic field, what you get from theorem CC above, this thing here, you get that for a cubic surface, the reduced Char group of zero cycles over a p-adic field is a finite group, because it's going to be covered by the X of K mod R for X of L mod R for finitely many extensions L over K. And each L over X of L mod R is finite. Now, this finite result for X of K mod R, in fact, it's a very general result, the one I mentioned for cubic surfaces. And this was the theorem of Collar in 1999, that if you take any smooth projective geometrically rational connected variety, then that set here is finite. And that theorem is proved by using these deformation techniques. So there's, for instance, some interest in trying to prove the analog of theorem C for other classes of rationally connected variety to try to get this finiteness here. However, this finiteness here is something which has been discussed in the literature, but not in all cases. So let me show you. If you take any smooth projective rationally connected variety over a field, the group A0 of X of Char group of degree 0 cycles by rational equivalence is killed by some positive integers. That's a general fact. And using algebraic case theory, the finiteness of A0 of X for rationally connected variety over the periodic field has been known for a while in some cases. So the case of geometrically rational surface, the group is finite. So I proved this in many years ago. And the proof is based on the Mercury-Sussin theorem and algebraic case theory. In arbitrary dimension, for varieties like this, okay, rationally connected variety over a periodic field, the prime 2p torsion of this torsion group is finite. That's a special case of a theorem of Tsuji Saito and Kanetomo Sato for arbitrary smooth projective varieties over a periodic field. So not necessarily rationally connected. And finally, in the good reduction case, with similar rationally connected specialization, the group A0 of X is 0. This is a theorem of Collar in 2004. So the part which is left open for this problem is the p torsion part for rationally connected variety, which could possibly be handled if we knew the analog of theorem C for this. Okay, let's go back to our topic. Do we have analogs of theorem C for other Pezzo surfaces? So theorem C was the one which told you about 0 cycles being spanned by 0 cycles of a small degree, or effective or rational or 0 cycles of degree big enough being rationally equivalent to effective cycles. Now, for the next two slides, which I wrote this morning, I computed this morning, I still have to double check the details of the computation. So let's look at the rational dipole surface of degree 2 with a rational point. So the statement which I have to double check is this: every effective 0 cycles of degree D. So I assume my dipole surface as a rational point. Every effective 0 cycle of degree at least 7 on X is rationally equivalent to an effective 0 cycle Z1 plus RQ, where ZR is positive and Z1 is effective of degree at least 6. This immediately implies that every 0 cycles of degree 0 is rationally equivalent to the difference of 2 effective 0 cycles of degree 6. In the proof, which is of the same style as the one we saw, or which I very briefly sketched, there are two special cases, as usual, just like in Corey's proof, where you have to pay more attention. Is the case where D is of this shape or that shape. In that case, one has to use curves with 1, respectively, 2 double rational points from the proof. Now, because we do not know the R density property for dipole surface of degree 2, and that we know the density property in almost all cases, but the R density property, I have no idea. The proof here for that one relies on Batteny over large field B, the combination of a reduction trick from K to K level minus T, and Collar's result on R density for geometric rational varieties. And now, we can also discuss dipole of degree 1. Now, there's a rational point there, the fixed point of the anti-canonical system. And if my computation is correct this morning, what you get is that every effective 0 cycles of degree at least 12 on X. I'm sorry, this is not 12. 16. This 12 should be 16. Yeah, on X, this is 16. Should be is rationally equivalent to an effective 0 cycle Z1 plus RQ with R at least 0 and Z1 effective degree at most 15. Every 0 cycle of degree 0 is equivalent to the difference of 2 effective 0 cycles of degree 15. Sorry for, I did write this too quickly. Anyway, the point is that one does find a bound. Okay. And again, there are two special cases which you have to look at, where you have to use curves with double rational points. And again, because we don't know the density, in that case, we don't know the density property at all, because we don't know if the depth of the surface of degree 1, which has a rational points, we don't know whether the rational points are Zariski dense. And even less do we know the R density property for such surfaces. The proof relies on these various results, which I just mentioned for the depth of surface of degree 2. Okay. So the proof result, now there's I have another result there, which is connected with cubic surfaces. So it's not, it's independent of the previous arguments, but the topic is very close. So let me discuss this one. And you may forget what you heard until now. Here's the theorem. Take a smooth cubic surface with no rational point. Then assume that any closed point of degree 3 on X is cut out by a line. Okay, so there are no, if you take a closed point of degree 3 and you don't find, you look at the, well, they can lie on a line, they can lie on a span of plane. No, you assume that they always lie on a line. And then in that case, there would exist a depth of surface of degree 1 over K such that this should be a Y, and this should be a Y, such that the rational points of Y are not Zariski dense. Okay, so if there exists a cubic surface with no rational point, such that all the points of degree 3 are cut out by lines, then somewhere there would exist a depth of surface of degree 1 where the rational points would not be Zariski dense. So the question of whether such surfaces exist was raised by Ma. And as I said, the question whether rational points are always Zariski dense and the depth of surface of degree 1 is a well-known open problem. So let me have one slide to give the height of the proof. You start with your closed point of degree 3, with a closed point degree cut out by a general line on P3. You blow up that point. So you get a fibration, W to P1, whose fibers are the sections of the cubic surface by the planes which contain L. And now, if any closed point of degree 3 on X was cut out by a line, you look at these curves of genus 1, you find that any closed point degree 3 on this curve of genus 1 would be cut out of a line. And so what this implies is that the Picard group of the fiber is reduced to the group spanned by the closed point P. Just so you think of your computer, it's very easy. If you have an elliptic curve in the plane, which has a closed point degree 3 cut out by a line, any other closed point degree 3 has to lie on a line, then you find that the Picard group is reduced to Z times P. And in particular, the degree 0 part of the Picard group of YT is reduced to 0. And now what you do is that you take your fibration, W to P1. So this is why I got mixed up with the W and the U, Y, I'm sorry. You take, so what is Y, what is, I'm sorry. This should be Y here. This is really Y. And then you take Y to P1. And then you take the Jacobian, you take the relative minimum model associated to the Jacobian allegoric fiber Y to P1. So you had this pencil of curves of genus 1. You take the Jacobian fibration and the relative minimal model of the Jacobian, the regular minimal model of the Jacobian fibration. And you compute and you see that in fact it is a depth of degree 1. And now if you take any point in P1K where the fiber is smooth, you find that because of this property, any K point of the fiber is a 3 torsion point. So that on your family of elliptic curves, all the rational points lie either in the singular fibers or on the closed subset cut out by the 3 torsion points. And so the total space of that relative minimal fibration is the depth of surface of degree 1 I was talking about. Sorry for mixing up the W and the Y. This will be corrected on the slides. I send the corrected slides. What's striking, in fact, here is that when you think about it, is that you produce lots of such depths of degree 1 where the rational is on the Zariski dense, because each time you take a line, you can do this such a vibration. So each time you take a line, you produce another depth of degree 1 with this property that the rational points are not Zariski dense. Okay, oh, sorry. I know how to fix this. Okay, so now I come to the conclusion. This should be the last slide. Yes. So theorem A, B, and C raise the following problems. So I go back to the main theme. And these problems are essentially solved in dimension 2, but they look very hard already for cubic hypersurfaces in P4 and for conic bundles over P2K. You take a field K, characteristic 0, and you take K bar to be an algebraic closure of K, and you consider a smooth projective geometrically connected variety, which geometrically is a rationally connected variety. Then the first question is that, is there an integer which only depends on the geometry, such that if X has a 0 cycle of degree 1, then X has close points of coprime degree at most n of X bar. Okay, this is what we have proved here. We haven't proved it for conic bundles, but for conic bundles over P1K, Cora and I proved that many years ago. Now, if you look at this question, you think, oh, but Colliot had some counterexamples. And so if you look at this paper of Colliot, the one which actually is the same as, well, anyway, in 2004, what you see that what it proves is that if you take quartics in Pn, n at least 4, there is no such universal bound which is independent of n. So you look at quartics, but the n grows. Okay, you can produce quartics in Pn, which have points in an extension of odd degree, very big, and no point in an extension of lower degree. But the n grows with this odd degree. Okay, so it's no contradiction with this question, with a positive answer to that question. And the second question, which is motivated by the theorems we've just seen, the theorem C, does there exist an integer m of x bar such that the Char group Cx0 of x is generated by close points of degree at most m of x bar? Okay, and again, this one here, for conic bundles over P1K, Cora and I proved that back in '77. Okay, well, that's the end of the talk, and thank you for listening.
Thanks a lot. Let's thank Jean-Louis. So are there any questions? I have two small questions. So first, did I get it right from the example by Kohler?
Can you speak louder? Can you speak louder?
Yeah, sure. It's about the example by Kohler and Mella.
Yes.
Did I get it right that number 7 is, there is still a possibility that number 7 is not needed in the previous theorem? There
is possibility, yeah.
So we don't have...
we don't know about 7. No, we don't know about 7. I mean, we're stuck in the proof in the same way, but we don't know about 7, no.
And another question.
So one thing I can say about this degree 2 business is that 2 and 3 is that in this paper by Cora, which I mentioned, we actually got similar examples for conic bundles over P1 with 6 geometric with k square equals 2. Okay, so with 6 geometric degenerate fibers or p-adic field, we had such examples where we had point of degree 3, a point of degree 2, and no rational point. Yeah. Second question, yeah.
And the second question, so like obviously there is no obvious way to produce a cubic surface which has no points of degree coprime to 3, but when the surface is non-minimal. For instance, you can just blow up a severe Brouwer surface, and this will do the job. And can one, do we have an examples like this when the surface is minimal?
You say no. I mean, you want, no, wait a minute. So you want no, okay, no point of degree prime to 3. Yeah, I mean, you want all the degrees to be divisible by 3, huh? Is that it, yeah? Well, yes, because of over the p-adix, we know that the answer to the problem is positive. Okay, so it's enough to produce a cubic surface of the p-adix which has no rational point. And so if a cubic surface of a p-adix has no rational point, that it has no rational point, then it has no rational point in an extension of degree prime to 3. That goes back to the, well, I mean, okay, that's proved by Corey. And it's very easy to produce such surfaces.
I see.
In fact, you can even produce such surfaces. I mean, you can produce cubic hypersurfaces in up to degree 9, which has no QP points. Smooth cubic hypersurfaces which have no QP points. Okay.
And maybe the last question. And so you told that Kohler had this semi-counterexample for quartic hypersurfaces.
But yeah, yes, they have for this counterexample. Yeah. Actually, it's a counterexample. I mean, it's actually not. It's not a counterexample to my question, but it's it's
kind of semi-counterexample.
Yeah.
And what's the state of art with high-dimensional cubics? If we just restrict to cubic hypersurfaces.
Well, it's open. It's it's open for cubic hypersurfaces. I'm pretty sure it's open.
For instance, we don't know anything in the.
No, we don't know. But so I mentioned cubic hypersurfaces. We don't know.
I see.
No, we don't. Yeah, you say we could go up, but yeah, I think we do not know. I'm pretty sure we don't know. I mean, I don't know offhand, and pretty sure we do not know.
Okay. So, any other questions?
Very general question. Are there non-trivial results in dimension 3, for example, for finite trifles?
Well, that's my question here. See, I'm taking the simplest. Okay, I can tell you something. I can tell you something about conic bundles over P2. Are you interested?
Oh yeah.
Okay. So there's a theorem which was proved by Zalberger. Unfortunately, it's in thesis and never published that part. That is, he tried to publish it, but the referee was stupid and rejected it, and then they never submitted it again. The theorem is that if you take a conic bundle over a curve of arbitrary genus, then there is an integer which depends on the genus and on the degree of the ramification locus, the geometric degree of the ramification locus, such that any zero cycle of degree at least equal to that integer is rationally equivalent to an effective cycle.
Mm-hmm.
Okay, that's the analog of what Corey and I did over P1. And in fact, it's a very interesting proof. I wish Zalberger would publish it one day, because it's a proof which is a very interesting proof, not a proof by going through this business of taking curves and then going down on genus. It's a proof by using Riemann-Roch for vector bundles on P1 for for Azumaya vector bundles on P1, and some Riemann-Roch theorem by Witt. Very, very beautiful proof. Anyway, so there is such a theorem. And so if you look at conic bundles over P2K, what I tried is the following. Suppose I have a close point of degree D on my conic bundle over P2K. Of odd degree. I project it down to P2K. Okay, so I get a close point of odd degree. Now, I may assume, otherwise, I mean, I can't reduce in degree, so I get a close point of a certain degree. The worst case is that the degree is the same as the one I started with. Mm-hmm. Now I have this close point of degree D in P2K, and I pick up a rational point on P2K. And I take a curve, smooth curve, I move the way we moved, of genus as low as possible, going to that close point of degree P and the rational point. Mm-hmm. And now I have a curve passing through this point and the rational point. And I restrict the conic bundles of a conic bundle of that curve. Mm-hmm. unfortunately, what happens, if I did the computation very quickly a couple of days ago, is that because the integer we're talking about depends on the degree the degree of the close point and the number of the degree of the variation locus, depends on the genus of the curve and the degree of variation locus, the integer one gets is too big for us to make a descent, to apply to be used in Zalberga's result and make a descent. Somehow one feels like it's, I don't know, anyway, it's like trying on the cubic hypersurface, making hyperpleasant sections, and then getting surfaces which are bad because they are of general type or something like that.
I see. Okay.
So I mean, you're welcome to try. It's quite exciting problem.
I agree. Thank you.
So, any further questions? Then let's thank John-Louis again.